All right, so welcome back. In our last lecture, we get started by talking about classical mechanics and also talking about work, which is a path integral. So remember, in the last example we did, we were talking about, first of all, you can do the calculation of work reversible equals to negative integral of PdV. Or the other way to put it is, in our last lecture, we write the change in your reversible work equals to negative PdV for closed system and reversible processes. And what we discussed is that the work itself is a path-dependent function. So depending on how the work is being done, whether it's isobaric followed by isochoric or vice versa, you might get different work for the process. Even if the initial state and the final state are the same, you might get different work. Now, example 2.9, and you will do more of these examples in your discussion session, is know how to calculate work for a known process, right? So for example, in this problem, we're talking about a non-ideal gas that's heated slowly. And whenever you say slowly, it basically tells you the reversibility. A process is super slow, in this class, means the process is reversible. And tells you the gas will expand reversibly at a constant pressure. So this defines the path of this reversible expansion of certain pressure and the volume change for the process. So this problem is a very straightforward problem, just setting up the problem as work reversible equals to negative from V1 to V2 PdV. Right, and pressure is a constant. It's basically taking the pressure out, or taking the difference between your final volume minus initial volume to calculate the work that's being done. So work is one of our path integral that we defined. Before we talk about the first law of thermodynamics, we have a second path integral we want to define. So that moves on to our section 2.3. So this is another path integral, which is heat. So this is the example we see in our first lecture, right? We're talking about a box of milk starting at room temperature and put it into the refrigerator. And with enough time, your milk temperature will equal to the temperature in your refrigerator, which is about like 4.1 degrees Celsius. So in this process, let's think about what is happening. So we have heat flowing from the milk, which has higher temperature, to the cooler. I guess I shouldn't say refrigerator, because refrigerator, you have things doing work to maintain the temperature. But now we have a cooler, right? It's isolated from the rest of the universe. Now the energy transfer between your milk to the cooler is the same as the heat absorbed by the cooler from the milk. So in this process, we can write out as heat equals to the small letter Q, which is mass of your cooler, C2, T2 minus T final, equals to mass of your milk times the specific heat of the milk times T final minus T1. Right, so in this case, you have three different temperature to keep in mind, right? You have initial temperature T2, which is the temperature of your milk, that's higher than your T final. That equals to T final minus T1 and times different specific heat. So this you should see in your previous classes. Now, in this process, whenever we use C2, C1, so these are our specific heat. Or specific heat capacity. typically, specific heat capacity or heat capacity is going to be a function of pressure and temperature. We will have a separate section discussing the nature of the heat capacity. But right now, let's just focusing on this relationship. Like what we're seeing in the pressure case, right? So in the work case, work is only defined for a process involving change. Like work, our heat is a line integral that's defined or only meaningful when we're describing a process. Now, the process we're talking about is not, instead of volume change in the work case, in this case, we're talking about temperature change. All right, so just keep in mind both work and heat, these two are line integral, and they're only meaningful when we're talking about change in different physical properties. If we limit ourselves to, say, constant pressure, for example, we can have derivative of QP equals to mass times Cp dt. So in this case, we're looking at infinitesimal changes of heat at constant pressure. Like, what exactly are we talking about? Now, this dQp term here, that's the infinitesimal change, amount of heat that's being transferred. Now, mass, that's the mass of the system we care about. Cp is a specific heat at constant pressure. And dt is the infinitesimal change of temperature. Right, so by writing it out, obviously we have a way to calculate heat, like what we did to calculate work. So that is taking the integral on both ends of this equation. And then this equation becomes the total heat flow, QP, equals to integral between T1, T2, mass times specific heat at constant P. So this little subscription tells you that's a specific heat at constant pressure, dt. Right, so since mass is independent from temperature change, normally you can take mass out from the integral, but it is not straightforward to just simply taking the specific heat out from the integral, since specific heat can be a function of temperature, unless we specify, like, keeping it constant. All right. And, well, this is a long question of an example problem, but if you read it carefully, effectively what we are saying is just telling you experimentally how are specific heats being measured, right? Specific heat of a material is an inherent property, and that's how people set up, like, drop calorimeter to measure the specific heat of a metal or of something else. So this is just the setup of the experiment. And what I want to note is at the bottom, it's like typically scientists can take multiple measurements so they know what is the specific heat at different temperature. And by plotting the specific heat versus temperature, they have a mathematical relationship. So you can find the workout version of this problem in our annotated notes. It's just plugging number and setting up the problem. It's just saying, like, hey, the total heat transferred from the system to the surrounding, which in this case, you can say the system is our metal and the surroundings of a water, right? So the heat transfer from the system to the surrounding equals to the heat transfer between, well, negative of the heat transfer between the surrounding and the system. So that's how we set up the problem. Or in the other words, we're just writing the mass of the metal equals times the heat capacity of the metal times the temperature of the metal, that's the initial temperature, minus the final temperature, which is after we drop it and it reaches equilibrium. And that equals to mass of water times heat capacity of water. And taking the negative, we have the final temperature minus the initial temperature of water. All right. So any questions on heat before we move on? Should be straightforward, but the take-home message here is to keep in mind that both work and heat, these are path integrals defined only for a change, right? So it doesn't exist a thing of the work of this cup that's not changing anything, right? It's just describing the thermodynamic state. It doesn't exist. Or the heat of the cup, that doesn't exist. It only exists when I have like 2 cups of water, I mix it together. Now there's a heat transfer for the initial state and the final state. Okay. If there's no question, we're ready to move on to our first law of thermodynamics. Let's see, lecture 4, let's get started. So in this section, we will spend a little bit of time talking about what is the first law of thermodynamics and what exactly do we get from the first law of thermodynamics. And then we'll talk about the definition of enthalpy. In the process, we'll also introduce new terms in thermodynamics like the state function, right? We talked about line integral, and now we're talking about a different kind of function, which is state function. So getting started. The first law of thermodynamics basically tells us there exists an extensive state function, E or delta E, which is the total energy of the system. All right, so in this definition, we have several terms you want to know. First of all, you have extensive. Remember, we have extensive versus intensive. Extensive tells you the value of this extensive property equals to the sum of the value of each part of that property, right? So it's straightforward to, hey, I have a small cup of water, I have a large cup of water. The volume is different, so that the volume will become an extensive property. Now, state function. This one is relatively new. State function tells us that the value of this function only depends on the current thermodynamic state of the function, right? So a state function tells you we're only talking about the specific state, the initial state and the final state, right? As long as the initial state and the final state are defined, these terms will always be the same. So volume itself can be a state function. We don't care how you get from point A to point B. As long as they are in the same thermodynamic state, they will have the same state function. Now, the first law of thermodynamics tells us there exists a state function, which is energy. And this energy, despite it being a state function, it is defined based on the sum of 2 line integrals. So the other way to put it, now the full version of our first law of thermodynamics tells us we have a extensive state function, which is energy. The change in energy between 2 different states equals to the sum of the heat transfer plus the work. All right, so delta E equals to Q plus W in a closed system without material exchange. And in here, Q, that's the heat flow into the system. Work is the work done on the system. So for thermodynamics, we always want to simplify our problem a little bit. So let's take one more step to simplify this total energy, because total energy consists multiple parts. So what do we know about total energy? So first of all, using our conservation of energy, we know that the total energy of your system, the change in the total energy of your system must equal, plus the change in total energy of your surrounding must equal to 0. That's the conservation of energy. You cannot destroy energy or create energy out of nowhere. And in addition, we want to simplify our total energy. So what we have is that total energy equals to mechanical energy and also internal energy. And for mechanical energy, we have kinetic energy plus potential energy plus internal energy. So kinetic energy and potential energy are the terms that physicists care more. We also went over like kinetic energy and also like what's the definition of potential energy when we discuss classical mechanics. But in thermodynamics, it's more straightforward for us to focusing on the physical chemistry nature of materials. So we focus more on internal energy. Right, so these are kinetic, potential. Later on, when we talk about statistical mechanics and Boltzmann distribution, we will talk about what are the internal energy, what's the molecular, what's the statistical mechanical picture of these internal energy and how can we derive it. But for now, just know that total energy equals to kinetic energy plus potential energy plus internal energy. And to save us a little bit of time, we can set our system to be something that is at rest and without external field. So when we make these assumptions, at rest tells us our kinetic energy equals to 0, and no external field, right? So no external electric field or gravitational field tells us our potential energy equals to 0. So for our thermodynamic system, we can further simplify this relationship into delta E, or the total energy of the system, equals to the internal energy of the system for closed, rest, no external field. For the system that is closed, it is at rest, it doesn't have any external field. So note that this relationship is only true when these assumptions hold true. So in our textbook, you will find lots of equations, right? So in different chapter, you'll find different expression of heat, you'll find different expression of internal energy or enthalpy. So it's very easy to get confused. So that's why we go slowly and just making sure you know that for every equation in your textbook, make sure you read the italic letter afterwards that tells you what are the assumptions we are making so that this equation stays true. Without these assumptions, that equation is not valid. All right, so for example, you might see a true and false problem and just say like, hey, delta U always equal to Q plus W for a closed system. Then it is going to be a false statement because delta U only equals to Q plus W if the system is at rest and also no external field. So these assumptions are important when we're looking at it. All right. And a few things that you want to keep in mind, like when we say positive and negative Q, so these are quite artificial, but that's how we define them in the conventional fashion. Whenever there is a positive Q or positive heat, it's saying the heat is flow into the system, right? Or you're expecting the system's temperature go up. Whenever you have a negative Q, we're saying the heat flow is from the system to the surrounding. Same applies to work. So when you have a positive work, we're saying the work is done on the system by the surrounding. And the negative work saying the work is done by the system on the surrounding. All right. So with the simplification, we can go back to our question, right? How do we calculate U? And, well, what exactly do we know about U using the conservation of energy? So in this case, if we're looking at infinitesimal processes, since U equals to Q plus W, or your derivative or the infinitesimal change of your internal energy, well, equals to the infinitesimal change of heat plus work. This is just an mathematical extension on what we showed. So, likewise, like your energy or total energy, our internal energy is also a state function. Right? So remember, what is a state function? We're saying the change of internal energy only depends on final and initial state of the system. All right. So if you think about it, this is a very powerful relationship we can use as scientists. Say, if we have a hypothetical cyclic process, so when we say a process is cyclic, we're saying the initial state and the final state are the same. And in this process, for example, we can keep it to be a cyclic isobaric process, like the pressure is the same, right? So we know the pressure is the same. We have a way to calculate the work that's being done in the process. We know the path for the work. But keeping the pressure the same doesn't tell us how is the heat transfer that's being taking place. But using the relationship of your total energy or your delta U only depends on initial and final state. So for a cyclic process, our delta U equals to 0, but it still equals to your heat plus work. So as long as we have a mean to calculate, say, work or heat for that cyclic process, we know the other, right? Even if the other path may not be very well defined. So it's a very powerful tool for us to use as scientists to calculate, well, one of these terms. And a few terminologies to keep in mind. Whenever we say something, we see this like delta U. Whenever you see this delta, it only tells us this is the final internal energy minus the initial internal energy, right? It's always final minus initial. And in this case, like the conservation of energy, whenever we have an isolated system, our delta U is also conserved, right? So in this process, for any processes, we say the energy plus of the system plus surrounding remain constant. But if we are looking at a isolated, at rest, no external field system, now your E just equals to your internal energy. Now your internal energy is also conserved for these isolated systems at rest. Yes?
For like small particles, when they move around and changes in temperatures, I usually think of that as kinetic energy, but here the changes in temperature.
So keep in mind, thermodynamics only cares about macroscopic properties. We don't define the temperature of, say, an electron.
Oh, I'm talking about like gas molecules.
It's the same, right?
Okay.
One single gas molecule is considered a microscopic object that you need to use quantum mechanics to discuss what is that gas molecule, right? So in thermodynamics, keep in mind, we only deal with macroscopic properties. All right, we don't look at thermodynamic properties of a single gas molecule. That's not a defined term. All right. Okay, so if we don't have any questions, let's look at some example problems together on the first law of thermodynamics. We will have more application of the first law of thermodynamics later on. So, getting started, the first question here, this is more related to the relationship we were talking about. What we have, a mole of water vapor initially at 200 degrees and 1 bar undergoes a cyclic process for which work equals to 338 joule. It doesn't tell us how exactly the work being done, but it tells us we know the work that's being done in the process is 338 joule. So this is a very straightforward problem. Whenever we say a cyclic process, we know that the change of your state function, in this case, we focus on internal energy, that equals to 0 for cyclic process. Right? And using our first law of thermodynamics, we have delta U equals to Q plus W in closed system. And in this case, we're specified that 1 mole of water vapor. It didn't tell us we have like chemical reactions taking place or material transfer taking place. It's pretty much assuming a closed system. And in this case, our Q just equals to negative W, which is negative 338 joule. Just using the first law of thermodynamics, nothing fancy. All right. Next question, this one, let's do it together on the board. It's asking us to calculate heat, work, and delta U, or the change in internal energy, when 1 mole of water is heated from 0 degrees Celsius to 100 degrees Celsius at a fixed pressure, 1 atm. So it's giving us the densities of water, and also it's giving us the heat capacity at constant pressure of water, and assuming our heat capacity is a constant. So in this process, it's asking us to calculate heat, work, and internal energy. And looking at the relationship, we have means to calculate our work and also heat transfer, so we can do it together. So in this case, it's focusing on heat first. We have Q equals to, so we're assuming our heat capacity is a constant, so that's more straightforward as mCp. So it's actually like the integral of mCp dt, but we know mass is a constant, Cp is a constant, so this just equals to mCp T final minus T initial, which equals to 1.00 cal per gram per degree Celsius times 18.0 gram, so that's calculated by 1 mole of water, times the 100 degree Celsius difference. You can also translate that temperature into Kelvin, but it doesn't change anything. It's a change in temperature. And this we calculate to be 1800 calories. So that's the heat. And then for work, well, so in this case, since we're talking about the change of your volume of the water in the process when we heat it up, it's the volume change is going to be a very small and also a super slow process. So we can use the work reversible relationship equals to negative V1, V2, PdV. So reading the problem, we're saying the pressure is kept fixed at 1 atm. So that is the negative P times V2 minus V1. The question didn't give us volume, but it gave us, we know the mass of the water, we also know the density of the water. So that gives us negative P times mass and 1 over rho 2 minus 1 over rho 1. All right, and then it's just plugging numbers. Now pressure is negative 1 atm times 18 gram and times, well, 1 over 0.9854 gram per centimeter minus 1 over initial density, 0.9998 gram per centimeter. You can do the calculation, but this gives us a super small number after the unit conversion, which is about negative 0.006 calorie. So we have work, we have heat, and then our delta U, or change of internal energy, equals to Q plus W, and that's just equals to 1800, where this one is negligible. All right. Yes.
The change in volume, I got it as a negative number, so wouldn't work be a positive?
Let me see. Yes, that should be a positive, but nevertheless, it is negligible. Yeah. Thank you. Any other questions? No. Okay. Yes.
So the units for work and heat will be the same?
Yeah, they should be, right? Because you're adding them together. So they should be of the same unit, which is the unit of energy.
So that can either be calories or joule.
Right, you have different ways you present your energy, right? So Newton meter is also a unit for energy, just depending on how you translate it. So on the algebra part, this section should be very straightforward. And on the conceptual section, let's spend a little bit more time looking at some of the true and false problems you might encounter in our chapter N problem. So for these true and false problems, you will see them in your discussion worksheet, chapter N problem, and also in our exams. So the key for these true and false problem is to read it carefully before you write down the answer and try to think about any assumptions they have made. So in this question, it says for every process, the change of system will always equals to the negative change of the total energy of the surrounding. So I'll pause and take polls from everyone, and then we'll go over every question here. So raise your hand if you think it is true. Raise your hand if you think it is false. Can't decide. You know, you can't write can't decide in your exam, right? But this one is a true statement. Now we're talking about the conservation of your total energy. We cannot create energy or we cannot destroy energy just from nowhere, right? So the total energy of your system plus surrounding, the change of your total energy must equals to 0. And by the way, this is in your textbook on equation 2.38. That's one of the equations that doesn't have any assumption. But it's good to be cautious because every time you see, like for every process, you have this kind of statement. Do make sure you read it carefully and make sure that it's a true, universally true statement, like the conservation of energy. Second one, for every cyclic process, the final state of the system is the same as the initial state. I'll pause for 15 seconds for you to think. Okay, raise your hand if you think it is true. Okay, raise your hand if you think it is false. And why do you think it is false?
Because no energy stays the same, but when I think of like the state of the system, I'm thinking of like pressure change, temperature. So that's why I did false, because the Q and W could be different.
Yes and no. So yes.
I said false because they like if it's cyclic, the whole thing has to be equal to 0, but that means they may be the same numerical value, but like one would be positive and one would be negative, so they're not exactly the same.
I see. So here the common misunderstanding is when we're talking about a cyclic process, it is defined. So the cyclic process itself is defined as the initial state and the final state being the same thermodynamic state. So when we say they be thermodynamically the same thermodynamic state, we're saying all the state functions are the same in a cyclic process in the initial state and final state. So these state function involves energy, yes, and also involves like volume, pressure. These are all like macroscopic properties describing a thermodynamic state, like pressure, volume, temperature. Those are the state functions we discussed already. We have internal energy, and later we'll discuss more state function. So for a cyclic process, this is also on your bottom of like page 49. So by definition, for a cyclic process, the final state and the initial state of the system must be the same. All right, so caring about the system, it is defined to be the same. So this one is also true. C, we'll have to like cross it for now because it is a little bit unfair. What the textbook wants you to know is like if we're only focusing on the system, now the same statement which is true for the system may not be true for the surrounding. And we will talk about more in why that is the case when we talk about the second law of thermodynamics. So I'll cross that one first for now. Okay, back to D. For a closed system at rest with no fields present, the sum Q plus W has the same value for every processes that goes from given state 1 to given state 2. All right, so I'm just going to write out what we have. So for a closed system, the assumptions we're making. So a closed system at rest, so this is kinetic energy equals to 0, and no field. So volume, not volume, potential energy equals to 0. I hate it when they use the same thing. So potential energy and kinetic energy both equals to 0 under the current assumptions. So what else do we know? We have the first law of thermodynamics, which basically say delta E, which equals to K plus V plus, delta K plus delta V plus delta U equals to Q plus W, right? So is this one true or false? So true to raise your hand. if you think it's true. Yes, so this one is true because we checked all the boxes of the assumption we're making. And we know that Q plus W gives us the state function, which is internal energy. Last one. If system A and B each consist of pure liquid water at 1 bar pressure, and if TA is larger than TB, then the internal energy of your system A must be greater than the system B. So what do we think about this one? It is more straightforward if we just look at, for example, what it is asking, right? It's asking about the internal energy. So now let's hypothetically thinking about a process of mixing these two systems together. Then thinking about whether or not that delta U is a positive or must be a positive or a negative process. So we have the delta U equals to Q plus W. And in this process, we know what Q is, right? We know that the temperature of your system A is larger than the temperature of your system B, given they're the same substance. However, we have no means to determine how well the work change when we're mixing these two systems together. We do not have enough information. So that tells us we have no means to say like, hey, the delta U must be a greater number for your system A.
So you said that because it doesn't tell us about a change in temperature, we have no way of knowing which Q is bigger.
So the process is we know what Q is. We know the heat transfer always goes from higher temperature to lower temperature. We just don't know how does the work change in the process. So we don't have enough information to tell specifically in what delta U is. So for trend force, always thinking about the extremes case. Like you have, what if you have these like extreme cases? That's all. Okay, we have 5 more minutes. So I'm just gonna get started in talking about enthalpy. And well, chapter 4 it's a shorter lecture note by design because I feel like I'm a little bit behind schedule. So we're catching up here. So enthalpy 2.5. So we went over our first law of thermodynamics, which defines a state function, total energy, which later on we translated into internal energy that we care more in thermodynamics. In addition, when we think about it, we know that energy or total energy or internal energy, heat and also work, they all have the same dimensionality. They are all some form or some defined by some processes of energy exchange. So in this case, later on, scientists defined a new state function, which is enthalpy H. So this is by definition equals to internal energy plus pressure times volume. All right, and we want to check our dimensionality. So what is our pressure over volume? Pressure is Newton per square meter times volume, which is meter squared. And that gives us Newton meter, which has the same dimensionality as energy. So what exactly is enthalpy? You can think about it as like scientists find it useful, like find that U plus PV appeared often when they do derivations. So that's why they start to define enthalpy. So in this case, when we're thinking about the physical meaning of enthalpy, we're thinking about hypothetically, we have an isobaric process. Now, enthalpy is uniformly defined as U plus PV. So this is just uniformly true. Note that we do not have any assumptions made after this definition. And we have this like straight lines tells you that's by definition, H equals to U plus PV. It's just true without any without any assumptions. But in order to gain more insight in what is enthalpy, we have to set some special case. So assuming a reversible isobaric processes, in a closed system. So now we are equipped ourselves with the first law of thermodynamics. We can write that delta U equals to U final minus U initial, and that equals to heat plus work. All right, so in this process, we're manually stating this is an isobaric process or constant P. We can write it as QP minus integral of V1, V2, PdV. So QP just say that's a heat transfer of the system in and out of the system at constant P. And then work is being calculated using the reversible, work reversible equals to negative PdV. So doing that calculation, we get QP equals to U final minus U initial plus, we're just moving this term to the left, this whole term, which is pressure times V2 minus V initial, or V final minus V initial. Just moving the entire thing on the left. And then in this case, since P is a constant, we can take it out from the integral. We manually set it to be an isobaric process. And then we can simplify the term a little bit. So the final goes with the final and initial goes with initial. So we got UF plus PVF minus U initial minus PV initial, or this equals to, this term is our H final. Remember the definition of my enthalpy equals to U plus PV, and this term is minus our initial enthalpy. Or the nature of our enthalpy is the heat transfer at constant pressure. Or the other way to put it is we talked about heat being a line integral. It is path dependent. But now if we specify it to be heat transfer at constant pressure, then our QP is defined by this new change of enthalpy. All right. So we will have more application of the first law of thermodynamics and also calculating different properties of like state functions in our next lecture. So I'll see our next lecture are like 2 lectures combined together because I don't know where we're gonna cut, but it's more gonna be a doing problems together kind of lecture. I also print out some like some copies of the blank note. So before you go, raise your hand if you want a blank copy of the lecture notes, so I know how many to prepare. So, okay, I'll do like 30, so hopefully it's gonna be enough. If you have your iPad, you can work on it as well. So our Wednesday and Friday, it's more like gonna be working on these problems together and use the terms we define. All right, good luck.